So hello everyone. Welcome to the afternoon section. So we're going to have 5 talks. So the first one is by Sean Watanabe, talking about bit security preserving hardness verification. Please.
Okay, thank you very much for the introduction. So this is a joint work with Kenji Atsunaga. So this is the outline of the talk. So first I briefly review background on bit security, and then I'll explain some motivation, and then move to technical result. Okay, so what is bit security? We shall quantify how much security a certain system provides. Roughly speaking, we say that the system is lambda bit secure if 2 to the lambda operations are needed to break that system. For instance, for the one-way function, if there exists an attack with cost t such that the success probability of inversion is epsilon, how much bit security is guaranteed? For this kind of search primitive, it is not difficult to define bit security. We can repeat this inversion procedure n times, then we can amplify the success probability roughly to n times epsilon. So if we want to make the success probability close to 1, the total cost will be t divided by epsilon. So by taking logarithm and optimize over adversary, we can define bit security. Until recently, there was no natural definition of bit security for decision primitive, such as pseudorandom number generator. In Eurocrypt 2018, Michiachi and Walter introduced a notion of bit security that is applicable to a decision primitive as well. And their definition was natural in the sense that it was compatible with some known facts. In 2021, we introduced an alternative notion of bit security, and it has clearer operational meaning. Later, we showed that the two notions of bit securities are essentially equivalent. More detail about relationship will be discussed in the next talk, I think. Okay, to explain some motivation of subtlety of bit security for decision primitive, let us consider security against PRG construction. So here we consider PRG construction from one-way permutation. So it is well known that if we append hardcore predicate to f of x, we can construct PRG. And when we discuss security of this PRG, we usually consider distinguishing game between PRG and true random number generator. For this game, we can consider 2 possible attacks. One is called linear test attack, and in this attack, by taking inner product with an appropriate vector, the adversary tries to detect the bias of the PRG. Another attack is called inversion attack, and in this attack, adversary first tries to invert the one-way permutation. Details of these attacks are not so important here, but for linear test attack, the output distributions of adversaries are balanced. On the other hand, for inversion attack, output distributions of adversaries are unbalanced. However, the standard advantage, which is defined as advantage over random guess, are the same for these attacks. So the standard advantage is not appropriate to capture the difference between these two attacks. Next, let me explain the framework of Michiachi and Walter. So in their framework, the adversary, in addition to 0 and 1, adversary may output bot symbol. This bot symbol means that the adversary gave up predicting the secret value. Then the bit security is defined as cost over this quantity, which we call conditional square advantage. And this quantity is defined as alpha, which is probability of non-bot times this, which is square of conditional advantage. For linear test attack, the adversary never output bot, so alpha is 1, and the conditional square advantage behaves as epsilon square. On the other hand, for inversion attack, if inversion fails, the adversary output bot, so alpha is something epsilon, and conditional square advantage is in the order of epsilon. So the conditional square advantage can capture the difference between these two attacks. In 2021, we introduced an alternative notion of bit security by formulating bit security as a hypothesis testing problem. And our characterization, our bit security can be characterized like this formula using some quantity, Renyi advantage, which is defined as Renyi divergence between adversaries' output distributions. Later, we showed that the two notions of bit securities are essentially equivalent by showing that conditional square advantage and Renyi advantage take the same value up to some constant. Okay, next let me explain the main topic of this work, which is hardness amplification. So we shall discuss hardness of computing some Boolean function by a Boolean circuit. We say that the function is S1 minus delta mildly hard if the success probability of computing f of x is less than 1 minus delta for any circuit of size S. Then we shall prove that XOR of k independent copies of this function is very hard to compute. In Yao's XOR lemma, we can show that the success probability of computing XOR function is less than half plus epsilon for any circuit of size S prime. Here, the circuit size is reduced by the factor of epsilon square over log 1 over delta. Because of this circuit size reduction, we cannot guarantee that the bit security is preserved in the hardness amplification. There might be some bit security loss that depend on epsilon. In this work, we derive hardness amplification result for Renyi advantage, and this result guaranteed that the bit security is essentially preserved. And to derive this result, we prove hardcore lemma for conditional square advantage. And to prove this result, we proposed a modified version of boosting algorithm with a bot symbol. So these are summary of our result. In more detail, we proved the following result. The Renyi advantage of computing XOR function is less than epsilon for any circuit of size S prime. Here, the circuit reduction factor is epsilon instead of epsilon square. One caveat of this result is that this theorem is only valid when the initial circuit size is sufficiently large. This is due to that we use weighted majority in the proof. By this theorem, we can guarantee that bit security is essentially preserved in the hardness amplification. The bit security loss does not depend on epsilon. Okay, to prove our result, we follow the hardcore lemma approach of Impagliazzo. So in the standard hardcore lemma of Impagliazzo, we can show that there exists hardcore distribution such that if input is sampled from hardcore distribution, success probability of computing f of x is less than half plus epsilon for any circuit of size S prime. Here, the circuit size reduction is epsilon square instead of epsilon. So this result is not enough to prove our result. So we derived a hardcore lemma for conditional square advantage. So in our lemma, we can show that there exists hardcore distribution such that if the input is sampled from this hardcore distribution, conditional square advantage of computing f is less than epsilon for any circuit of size S prime. Here, the circuit reduction factor is epsilon instead of epsilon square. Okay, so there are two approaches to prove hardcore lemma in the literature. One is based on minimax theorem, and the other is based on boosting algorithm in the learning theory. And because it is difficult to apply minimax theorem in our setting, so we proved our result by proposing modified version of boosting algorithm with bot symbol. Okay, there is an alternative motivation of our work. In the context of Gold-Reich-Levin theorem, in 2004, Hurst proposed a modified Goldreich-Levin algorithm by taking into account an adversary which may output bot symbol. And he evaluated the performance of his algorithm using the conditional square advantage. And so it is natural to consider hardcore lemma for conditional square advantage as well. However, one difficulty is that in the context of the Goldreich-Levin theorem, the bot symbol plays a role of erasure symbol in the list decoding interpretation of the Goldreich-Levin theorem. On the other hand, in the context of boosting, the role of bot symbol is not so clear. Okay, so this is the outline of our modified boosting algorithm. So first, we assume existence of weak learner such that conditional square advantage is larger than epsilon. And by using those weak learners, we update the distribution in a similar manner as the standard boosting algorithm. And so in this boosting algorithm, the bot symbol does not appear explicitly. However, this update weight must be chosen very carefully by taking into account the probability of non-bot. Roughly, in our algorithm, we put more weight if probability of non-bot is smaller. So roughly, we can say that the untalkative weak learner is more reliable. Okay, so this is a concluding summary. When we discuss bit security, instead of the standard advantage, it is more appropriate to consider conditional square advantage or any advantage to capture the difference between balanced attack and unbalanced attack. For balanced attack, the bit security of our XOR lemma is the same as the bit security of the standard XOR lemma. However, for unbalanced adversary, the bit security of our XOR lemma is improved from the standard XOR lemma. There are a few open questions. One is, can we prove a uniform version of hardcore lemma for conditional square advantage? And another is the circuit size loss of epsilon in our hardcore lemma for conditional square advantage. Is it unavoidable? Okay, thank you very much.
Any questions? Oh, okay. Okay, I will try to ask a question. Hopefully it's not difficult. So you said you come up with the new hardcore, you prove it by come up with a new...
hardcore lemma?
By proving using, get a new learner, like learning algorithm, right?
So sorry, what?
You get a new learning algorithm in order
learning
to,
algorithm, yeah,
to
yeah,
prove your
yes.
hardcore lemma. Does that has anything said anything about in the learning literature? Does it give anything new there?
You mean any consequence in the context of learning theory? So I'm not sure if learning algorithm with bot symbol is so common in learning literature, but if we have a weak learner with that may output bot symbol, so bot symbol means that weak learner is not so confident about output. So in the context of learning theory, we usually consider learners that only output 0 and 1. But if weak learner is not confident, then if the weak learner output bot symbol, then that information can be used to reduce the number of invocations of weak learners, and we can improve the performance.
I see.
Yes.
Great. So the main, like one of the key ideas, like for bit security, explore the setting where you output bot, right?
Yes.
Do you think there are other applications, like in other, like you said, maybe in crypto, we can better capture the security for PRG, and for learning, and you can also explore that, get some like better learning algorithm. Do you think you can apply also to other places, or this idea of like?
You mean other than cryptography and learning theory?
Anything, yeah.
Anything, any other other context we don't know, but yeah, hopefully we want to extend this idea for more complicated cryptographic primitives, such as construction of a PRG from a one-way function.
Oh, I see.
But the construction of a PRG from one-way function, there are a lot of other difficulties. So yeah, we don't have any concrete result yet.
Okay, thank you. Yeah.
Thank you.
Thanks very much.